Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes, 3rd edition, and we're doing problem number 4.2. The problem statement says, a liquid phase chemical reaction, A goes to B, takes place in a well-stirred tank. The concentration of A in the feed is Ca0 in moles per meter cubed, and that in the tank and outlet stream is Ca in moles per meter cubed. Neither concentration varies with time. The volume of the tank contents is V in meters cubed, and the volumetric flow rate of the inlet and outlet streams is V dot in meters cubed per second. The reaction rate, the rate at which A is consumed by reaction in the tank, is given by the expression R in moles of A consumed per second equals K times V times Ca, where K is a constant. Then they give us this diagram here of the tank. A goes to B, and you have water flowing in at the top, or whatever this reaction concentration mixture going in at the top, it's stirred, and then it comes out the bottom here. Part A. Is this process continuous, batch, or semi-batch? Is it transient or steady state? This is a continuous process. You have a steady flow in and a steady flow out. That's the definition of continuous. Is it steady state or transient? Well, they said everything is remaining the same. So you don't have a variable concentration of A in the tank. It's always Ca. You have the same concentration of Cb in the tank. You have steady flow going in, a steady flow going out. There's no level change in the tank or anything like that. So it is steady state. Even though there is a reaction going on in this vessel, it's still at steady state because the reaction isn't changing with time. The reaction rate is constant. This is the reaction rate that they gave to us, or the reaction law for this particular species. All right, part B. What would you expect the reactant concentration Ca to equal if the reaction rate constant equals 0, or there's no reaction? What should it approach if K goes to infinity? Infinitely rapid reaction. Okay, let's see this one first. If K equals 0, then this rate equals 0. So that means there's no A changing with time. So no A is going to B. Then the concentration won't change. So the concentration in the tank will be the same as the concentration of the stream going in. Now, on the other hand, if K goes to infinity, that means R is infinite. So anything that it goes into the tank is immediately converted into B. All of it immediately goes to B. Well, then Ca goes to 0. It doesn't go negative because you can't have a negative amount of A, right? But all of the A turns into B. Now, if you have a reversible reaction, this is just a little extra that I can tell you guys about. If you have a reversible reaction where B can go into A and then A can go back into B, and it kind of depends on an equilibrium constant, then the rate law would look different than it does here. So no B, once A turns into B, there's no going back in this rate law. In this rate law where A goes to B, no B goes back into A. And so there's only one way for this A to go, and if the rate is infinite, then immediately all the A goes to B and B doesn't come back. And so it is feasible that you would reach 0 concentration of A in this case. Part C. Write a differential balance on A, stating which terms in the general balance equation accumulation equals input plus generation minus output minus consumption. You discarded, and why you discarded them. Use the balance to derive the following relation between the inlet and outlet reactant concentrations. As you can see here, there's no generation in the tank of part A. There is of part B, but there's none of part A. The element or chemical A is not generated. It's only consumed. As I kind of talked about before, it doesn't come back. Okay? There's no accumulation of A in the tank. This is a steady state process. So there's no time dependency of the concentration of A. So any change in concentration with time would make this a non-steady state process. So accumulation is 0. A is consumed with time. That is defined by the rate law that they gave to us. And obviously the in and out concentrations with time were also given to us in the problem statement, so those are defined. So what does that look like? This is in minus out, and then I moved consumption over to the right hand side, which is R. Okay, so we substitute in all of these numbers, well, not numbers, but we substitute in the rate law in for R, and then we solve for CA, combine like terms, and do some simplification, algebraic stuff. You guys know how to do that. Okay, so let's examine this equation and verify that it matches part B. Okay, so in part B we said that if K is 0, then the reaction, or then the concentration in the tank should go to Ca naught. Now let's see if that's true. This is 0, then that means this whole term is 0. That means we'll get Ca divided by 1 equals Ca naught. Okay, yeah, so Ca equals Ca naught. That's what we predicted. Ca equals Ca naught. Okay, now let's find out. Okay, K goes to infinity. Okay, K goes to infinity. That means this number is very, very big, plus 1. Okay, so infinity plus 1 is just still infinity, right? So K naught, or Ca naught divided by infinity, Ca naught divided by infinity, well, that is 0, right? Because you divide by a big enough number, it's just going to get closer and closer and closer and closer to 0 until, yeah, basically it approaches 0. Isn't that what we said? Yes, Ca naught goes to 0. That's what we expected. Great. So this equation that we found out from our analysis seems to match our common sense here as well. So, well, that is it for problem number 4.2. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.